We have a glucagon to talk about. I mean, glucagon will prevent the glucose uptake. Okay. You can see, how decreased blood glucose elevates blood glucagon on this image, this graph. Okay. It's a protein, it's a water-soluble hormone, binds to the receptor. And interestingly, it stimulates two pathways that we learned about. It stimulates cyclic AMP, and it stimulates phospholipase C. Okay, so adenylate cyclase produces cyclic AMP, phospholipase C produces IP3 and leads to the calcium release from endoplasmic reticulum. In terms of the effects, how can you increase blood glucose? Remember we talked about how can you increase this, how can you increase that. One of the methods that we mentioned, you have to excrete less. Here's the trick. In a healthy person, we do not excrete glucose. If somebody has glucose in the urine, it's a sign of disease. Glucose is not supposed to be there unless you, I don't know, overload it yourself. I don't think even Cheesecake Factory can do that much glucose, really. Okay? So you can only make more. And two major sources of glucose, glycogen, so break down glycogen in the process of glycogenolysis, and synthesis of glucose from scratch in the process of gluconeogenesis. You may ask, what lipolysis is for? You can break down fats into the free fatty acids and glycerol, and then you can convert glycerol into one of the intermediates of glycolysis and run glycolysis backwards. You can convert glyceraldehyde 3-phosphate back into glucose, or you can take fatty acids. That's not going to be on the exam. Don't worry about that part of biochemistry. We'll talk about it more when we'll get to the digestive system. But just fatty acids, you can break them down to acetyl-CoA, make pyruvate out of it, and from pyruvate make glucose. Okay? So fats, very indirectly, but you can, after a lot of bells and hoops, convert into the glucose. But the most direct, of course, glycogenolysis, that's the best, and gluconeogenesis using intermediates of the Krebs cycle. And any process that will be a glucose utilization, use of glucose, like glycogenesis or glycolysis or lipogenesis, all these processes will be inhibited by the glucagon. Does that make sense? Questions? Moving on. Male versus female gonadal hormones. We learned them twice. And this time it's going to be fairly straightforward, fairly simple. We're not going to focus. Male hormones are regulated very simply. Females are the ones that give the most troubles. Okay? Because females establish absolutely amazing cycle. Males are just, you have an axis. Again, look at this. Hypothalamus produces gonadotropin releasing hormone. Gonadotropin releasing hormone reaches anterior pituitary, which produces two gonadotropins, follicle stimulating hormone and luteinizing hormone. What is the function of follicle stimulating hormone? It's kind of in the name. Stimulate follicles, yes. Follicle stimulating hormone in males stimulates the development of sperm. Okay? So like in female, follicle gives rise to oocyte. in males, I mean, we don't have follicles, but you can, like, follicle is something like circular, sperm is somewhat, circle, just to make an association. So follicle stimulating hormone will act on a part of the testes that are called seminiferous tubules and will stimulate sperm development. Luteinizing hormone will act on so-called Leydig cells, which will produce testosterone. Now, testosterone is necessary for sperm production. Does that make sense? So there's actually a communication. They both are required. There's no testosterone, sperm cells will not, spermatocytes will not develop. We good? Got it? Another hormone that's produced in seminiferous tubules is inhibin. Okay, so this testosterone and inhibin are called gonadal hormones. So both testosterone and inhibin via negative feedback loop will act on hypothalamus and anterior pituitary, and testosterone and inhibin will block the release of gonadotropin releasing hormone and the release of gonadotropins. Does that make sense? Remember, we pictured before the hypothalamus pituitary thyroid and hypothalamus pituitary adrenal axis. It's the same three-step axis. Hypothalamus, releasing hormone. Pituitary, tropic hormone. And then you have final gland at the bottom. In this case, it's testes, which produce gonadal hormones. Okay? Does that make sense? Now, run this axis. As it goes and stimulates, what's going to accumulate in the testes? Sperm. Sperm's going to accumulate in the testes. And the more sperm accumulates, which two hormones will be produced more and more and more? Testosterone and inhibin. How is it going to affect hypothalamus? It's going to inhibit it, so the whole axis shuts down. So sperm is not produced like over, okay? So every time there is a ejaculation and sperm counts decrease, pretty much you restart the axis, okay? So it starts, levels of those hormones go down, the axis starts. Make sense? Now, there are many molecules that can be involved, and by the way, in the right bottom corner, you can see that Leydig cells that produce testosterone, they act on the seminiferous tubules to promote spermatogenesis. But there may be more than that. There are probably other hormones involved. Okay? What I want you to know, testosterone is needed for spermatogenesis. All those other, it's fun, but let's not spend too much time on it. Question? We good? Testosterone has full body effects. It is anabolic hormone. It increases BMR. We're going to talk more when we get to the reproductive, but pretty much you get a spike of testosterone during the intrauterine development when there's a decision, boy or girl, pretty much boy, okay, boy, finally. And there is a steady increase in puberty. Testosterone goes up, and that increase in testosterone leads to development of external genitalia, development of the hair, armpits, groin area. Skin becomes more oily due to the sebaceous gland activation. Bones are going to grow. That's the puberty growth spurt. Boys become, well, I would say, sexually reproductively competent. Okay, so sperm is effectively developing, semen is effectively developing, libido increases, muscles grow, and voice deepens. And it's I coach soccer team, and I coach pretty much U14, U15 team, and it's so funny to look at the kids. Some of them, they went into that growth spurt, and you can see them becoming progressively bigger, stronger, and it associated with the voice lowering. And some of them still have kids' voice, and they're smaller. You see 100% correlation. Okay. Now, questions. I mean, general idea about anabolic effects. And testosterone, if you decide to use it as the PED, performance enhancement drug, it's a lousy idea. Liver is going to convert it to estrogen. So, a lot of, surprising outcomes. Female hormones. Let's do this. Seriously, because we're going to dig deep into it when we get to reproductive. So let's do this. You will learn sort of a metabolic effects. Okay? But this whole cycle we will leave for reproductive. It's really too much to eat right now. Okay? I still want you to know that females, the very beginning in females is the same. So you start with hypothalamus that produces gonadotropin releasing, which acts on the pituitary, which produces gonadotropins. And then things become interesting because first it stimulates ovaries to release estrogen or estradiol. I prefer estrogen, they're synonyms. Okay? So luteinizing hormone stimulates estrogen. Follicle stimulating hormone stimulates follicles. Estrogen is needed so follicles become sensitive. Does that make sense? So follicle stimulating hormone slowly leads to the growth of follicles. Luteinizing helps it. And at this point, so far, that's still negative feedback. So if you would look at the levels of hormones, they're fairly steady. They grow very, very, very slow, the levels. Because at this point, okay, it's kind of, I just like the physiological part of it. I'm not going to test you on all those different steps. But look at this. This is awesome. Estrogen will inhibit anterior pituitary and hypothalamus at this point. Does that make sense? So they're all in control. Follicles grow slowly. And then, right before the ovulation, there's a surge of estrogen from the follicle, okay, which changes the feedback between the ovaries and the anterior pituitary from negative to positive. And instead of inhibition, at this point, estrogen leads to the surge in luteinizing hormone. More luteinizing hormone is produced, more estrogen is produced. More estrogen is produced, more luteinizing hormone is produced. On the hormonal profile, right before the ovulation, you will see it as a huge spike in estrogen and luteinizing hormones levels. Okay? Surge in luteinizing hormone leads to ovulation. Okay, so oocyte leaves the follicle. Follicle is empty. Empty follicle turns into the corpus luteum, the yellow body. And corpus luteum keeps producing estrogen, and what's important, progesterone. The role of progesterone here, if oocyte that was released from the follicle becomes fertilized, this is not on the exam. I'm just giving you a sense of what's going on. So you can actually, many of you can relate it to the changes in your body. Okay? So progesterone prepares the uterus for the implantation of fertilized egg. Fertilized oocyte, sorry. Well, egg, yeah. When it's fertilized, it becomes egg. Does that make sense? So, let's say no fertilization. If there is no fertilization, no implantation, progesterone will decrease, and we'll get to that. So, at this point, elevated estrogen and progesterone reestablish negative feedback, and they inhibit hypothalamus and anterior pituitary. Does that make sense? So I have negative feedback in the beginning, positive feedback in the middle, negative in the end. So at this point, levels of gonadotropin releasing hormone, luteinizing hormone, and follicle stimulating hormone, they all decline, which acts on ovaries, which leads to the regression of corpus luteum. Since corpus luteum is the major source of estrogen and progesterone, and it regresses, now levels of estrogen and progesterone start to decline. Does that make sense? As they decline, these guys bounce back, and the cycle starts again. So that's ovarian cycle. Does that make sense? So, how does the contraception work? You take progesterone. Constant, fairly high levels of progesterone. Well, let's put timed levels of progesterone. They keep inhibition of gonadotropins and gonadotropin releasing hormone. So they essentially constantly keep your organism at the end of the cycle. So there is no follicle maturation and no ovulation. Does that make sense? That's it. Now, what I want you to know for the exam, that if I ask you which of the female hormones can inhibit gonadotropins or gonadotropin releasing hormone, you tell me estrogen or progesterone. Do I make sense? Which of the hormones will stimulate ovaries directly? You tell me FSH or LH. Okay? I'm not going to ask you about this cycle. We'll have a chance to talk about it. Am I clear? Awesome. Whole body effects, it's anabolic in females, development of sex characteristics. Progesterone is actually very important for carrying the baby. For instance, it decreases the movements of uterus, okay, which is critical, really, because baby is not expelled before the term, right? Estrogen is really important for calcium metabolism. That's why females after the menopause often experience osteoporosis. Calcium uptake is decreased. And after the menopause, risk of atherosclerosis in women goes up quite dramatically because estrogen, turns out, regulates cholesterol levels. That makes sense? Now, these are kind of boring. Small pineal gland. We still have no idea how it works. Any questions before moving to pineal? Pineal gland, small gland, part of the epithalamus. About small, just small, okay? Just small. Right here. In adults, it slowly fibroses. Produces the hormone called melatonin. I always say it's the hormone, one of the few things that you can buy over the counter in a food supplements in the pharmacy that actually works. It's a hormone that helps you to regulate sleep-wake cycle. It's not the only one. I mean, it's not the only mechanism for the circadian rhythms. Last year, Nobel Prize in Physiology and Medicine was for circadian rhythms regulation. So melatonin is just one component. Works very easy. When there's light, this light signal goes into the suprachiasmatic nucleus of the hypothalamus. And then the neural signaling via the brainstem inhibits melatonin production. When it becomes dark, no light, no inhibition, melatonin levels increase. You feel sleepy. That is it. A friend of mine spent several weeks beyond the polar circle. There's like polar day, polar night, you know, like extend when there's no real night. So she said that it totally messed up her sleep. So you can be, like, it's 2 a.m. in the morning, you're out there, and it's like this, maybe a little bit darker than this, what's now outside. Okay, so you're drowsy, but you're not really sleepy. It's really hard to fall asleep. Melatonin does work to, say, adjust to jet lag, okay, or just get a good night's sleep. It's pretty safe. The only thing, if you go in to take like a 4-hour sleep, probably not a good idea. I did that a couple of times. I took melatonin, slept 5 hours. I wake up, I feel like I've been knocked out just recently. Okay, really, just you're drowsy. Okay, know the function. Good. Moving on. Thymus. Pretty boring gland too. Produces thymosin, thymolin, and thymopoietin, 3 hormones that regulate maturation of T cells, immune cells. That's all you need to know. Know the names of these hormones and T cell maturation, lymphocyte maturation. Okay. Does that make sense? Now we're talking about secondary endocrine organs. Some of them we already mentioned. As I said before, these guys are, what should I call them? Oh, they have another major function, like heart. Pumps blood. It also produces atrial natriuretic peptide. We talked about it. Somebody has high blood pressure. Atrial natriuretic peptide goes up. One of the effects is vasodilation. Okay, blood vessels dilate, pressure drops. Another effect, renin production goes down. Remember renin, angiotensin, aldosterone system? Renin goes down, aldosterone goes down, eventually, after angiotensin. When aldosterone goes down, what's the what is the ion that aldosterone retains? Normally, aldosterone retains the ion that is followed by water, sodium. Since aldosterone is low, sodium stays in the urine. Since sodium is in the urine, water is in the urine, you produce large amounts of urine, you decrease the blood volume. Does that make sense? You decrease the blood pressure. It's kind of straightforward. If it's produced, and the title tells it, natriuretic, okay? Natriuretic means sodium in the urine. Questions? No, we good? Stomach. I'm going to mention them very briefly, really, because we're going to focus on those hormones when we'll get to the digestive. Gastrin, histamine, and ghrelin. Stimulus for them is food. Okay, food gets into the stomach, except for ghrelin. We'll get to. Food gets into the stomach, gastrin and histamine are produced. What do you think they do? Overall, I mean, hydrochloric acid, blah, 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 gastric motility. What is that? Increased gastric motility, huh? Digestion. Think about this. The change that happens in the stomach is food. How can we get rid of that change? Digest the food. So gastrin and histamine will stimulate digestive activities. Does that make sense? Good. Ghrelin is the hunger hormone. When your blood amino acids and blood glucose falls, ghrelin is produced and increases, leads to conscious perception that you're hungry. Okay? We good? Clear? Okay. Make your life a little easier. So these two, those are duodenal hormones. Most important, probably. Secretin and cholecystokinin are produced in response to food coming into the duodenum. What is the outcome? What do they stimulate if they're produced in response to food? Digestion. We're going to address which exact mechanism. Digestion. Okay. Cholecystokinin will stimulate bile release, so it's pretty much, it's responsible for taking care of fats. Secretin is responsible for taking care of spillover acid that comes from the stomach. Okay. Gastric inhibitory polypeptides and glucagon-like peptides, they are two insulinotropic hormones. Okay? They're produced in a small or large intestine. So GIP produced in the small intestine, glucagon-like peptide is produced in the large. I'm not going to trip you over asking, is it produced in the ileum, duodenum, jejunum, or colon? Don't worry about this. I want you to understand that all these four are intestinal hormones. Now, what is the reason? Give me a reason why GIP and GLP are insulinotropic. Why do they stimulate insulin secretion? What do you think? Go ahead. Bingo. It's food in the intestine. It's about absorption of nutrients is about to happen. Your blood amino acids and glucose levels are going to go pretty soon, going to go up. You want to get insulin out. Make sense? That's, I mean, anything insulinotropic is jumped on because it may be a diabetes cure. Good. This, so effects, digestion for GIP and GLP, they are insulinotropic. Okay? And look, anything that, will stimulate. Kidneys, renin. Low blood pressure leads to production of renin. Renin will eventually, bless you, bring up angiotensin II. Angiotensin II will stimulate aldosterone. What is the effect of aldosterone on the blood volume? Increases. Increased blood volume corresponds to increased blood pressure. So renin, angiotensin, aldosterone system called RAS, it's actually like an acronym for it. It's one of the major long-term renal responses to low blood pressure, if not major long-term renal response. We're going to see the system again and talk more about it and pause on it better in the renal section of the course. But at least now I say renal regulation of blood pressure later, you have an idea what's, I say renin, you have an idea what's going on. So what you need to know, low blood pressure, renin. I will merge angiotensin 1 and 2 in angiotensin, okay, aldosterone, and then all the effects of aldosterone that we discussed. We clear? Erythropoietin. Kidneys produce erythropoietin in response to hypoxia. Erythropoietin stimulates production of red blood cells in the bone marrow. You have a lot of red blood cells, they can carry more oxygen. Okay? So, what is you may have seen athletes that have masks, especially like indoors when they run in the treadmill, they can put a mask and regulate the amount of oxygen that they inhale. And it's a legal way to boost the number of red blood cells in the blood. If you go to like any mountainous region, like not Pennsylvania, something like Colorado or Alaska, high, okay? The concentration of oxygen becomes lower, and first quite a few days you feel very poorly. You have hypoxia. When you come back to the plains, your VO2 max is just incredible. Because while you were feeling hypoxic, your red blood cells, your kidneys, churned out erythropoietin. Erythropoietin stimulated red blood cells in the bone marrow. And you increased your red blood cells levels. They will come back eventually. That's why endurance athletes, most of them, they train in the places like Utah, Colorado, California, wherever they can get higher in the hypoxic conditions. And it's pretty, let's admit. Just awesome to be there. Does that make sense? Again, low oxygen, EPO, a lot of red blood cells, oxygen transport to the cells is restored. Bones. On the fairly brief level, FGF23 stimulates the excretion of phosphate, okay, and decreased vitamin D. It's probably a part of calcium regulation. Osteocalcin another insulinotropic hormone. Now it increases insulin. That's all I want you to understand. Okay. FGF23 phosphate regulation, osteocalcin, insulinotropic. Some of those hormones were discovered not that long ago. So scientists haven't quite figured out how they do it. What are the mechanisms? Skin, that's pretty simple. Vitamin D. Another name for it, vitamin D. Another name is cholecalciferol. Helps to absorb calcium in the intestines. That's all you need to know. Okay? Yes, it is. Parathyroid hormone helps to activate, okay, vitamin D in the kidneys. So know this. Know this function of parathyroid hormone, all right? That makes sense? Do you understand what I'm asking? Please, parathyroid hormone helps to activate vitamin D in the kidneys. Activated vitamin D helps calcium absorption in the intestines. Good? Liver, insulin-like growth factors. We covered them extensively. Just remember that IGFs are produced by liver and inhibit growth hormone. Both pituitary production and the upper level hypothalamus. So inhibit growth hormone releasing hormone and stimulate growth hormone inhibitory hormone. Angiotensin is also produced by the liver. Again, we run into the renin-angiotensin-aldosterone system. Again, you have a question, which hormone does liver produce? You see angiotensin? That's the answer. A lot of it is just cross-references, as you can see. Liver also produces thrombopoietin, okay, which is pretty interesting. Think about this. So thrombopoietin is bound to platelets normally. When patient develops low platelet counts, newly synthesized thrombopoietin in the blood cannot bind to anything. Does that make sense? So you have low platelets, the amount of unbound thrombopoietin in the blood automatically increases. That stimulates platelet production. Platelet numbers go up, thrombopoietin binds to the platelets, it's not signaling anymore, it's not free, and that's your negative feedback. Does it make sense? So if your liver is gone, your coagulation is gone. If liver is gone, you're pretty much like you're dead in 18 hours. Seriously. We're talking about complete obliteration of liver. It's one of the most critical organs. Hepcidin regulates iron. Why it's so important? Iron is a critical nutrient for a lot of bacteria. If you reduce iron in the blood, you reduce the ability of microorganisms to grow in your blood. Does that make sense? So again, these are introductory. This is my favorite. Leptin and adiponectin. I will start actually with adiponectin. We're going to talk about this and wrap it up. So, adiponectin, I worked in this. It's freakishly expensive to obtain. It's like nanograms were like $400. It's just unbelievably expensive. We thought about doing some experiments on mice with adiponectin. We had to quit initially. We had to wait till the price comes down to something we can pay from the grant. It regulates energy metabolism. How? We have no idea. What we know about adiponectin is that it is generally anti-inflammatory. Okay? It is anti-inflammatory, decreases activation of macrophages. It is cardioprotective, very much cardioprotective, which means it will decrease the manifestations of atherosclerosis. It will decrease the problems with cardiomyocytes, cardiac muscle. So pretty much it's good. Okay? The interesting thing is, if you would look at chronic inflammatory diseases, such as atherosclerosis, or type 2 diabetes, or obesity, in people with those conditions, what we may call acquired lifestyle conditions, adiponectin would be low. Does that make sense? So if you will, like in mice, if mice are diabetic, you give them adiponectin, they lose weight, and their cardiac symptoms, they become better. Okay? You just take any diabetic mouse, you look at levels of adiponectin, they low. The interesting point is, if you take sort of genetic autoimmune inflammatory diseases, like rheumatoid arthritis, it's inflammatory disease. Adiponectin levels should be low. No, they are actually like super high. Mechanism is unknown. One of the hypotheses. This disease is not it's not acquired. It's intrinsic disease. It's a disease because your immune system went nuts. So organism tries to protect by producing anti-inflammatory chemical. Well, anti-inflammatory hormone. It doesn't work, but it keeps producing. Like remember in goiter, we talked about goiter, you have those antibodies, they just keep churning out thyroid hormone. You can lower TSH as much as you want, thyroid hormone will still be produced. Does that make sense? So, I mean, there are a lot of experiments on mice showing that adiponectin is cardioprotective and, prevents atherosclerosis and stuff, but it never translated to humans yet. Now, my favorite hormone, leptin. I always say that that's pretty much the only hormone which action we can consciously overcome. Like if you produce growth hormone, you cannot just say, I stop growing. Just no, okay? Or, testosterone to a certain extent. But like, if somebody produces testosterone, you can't tell your testis, like, no more sperm. That is it. That's enough, okay? It's going to happen, okay? Leptin has main function is to tell you when you're full, when you had enough to eat. It never works, doesn't it? I mean, that's good. That's enough. That's why we order one large pizza from Papa John's, not two. Okay, because you order two, you're going to finish. You order three, we're going to finish 3 pizzas as a family. Okay, it's disgusting, but we're going to do it. So leptin is produced by adipose tissue, and it decreases appetite. And it acts on receptors in hypothalamus. Okay, and decreases the sense of appetite. But interesting thing. So you would say, okay, if you eat initially, the more adipose tissue you have, technically the more leptin you should produce. But the more leptin you should produce, well, all in all, in obese people, leptin levels do not change much independently of whether they're eating or not. It's now proposed that in obese people, if you constantly overeat, you develop leptin resistance. That signal that you're full isn't working anymore. So leptin is produced, but your appetite is not decreased. So even when obese people do not eat, they still have very high leptin levels. That makes sense? Now, to give you an idea, and pretty much leptin and ghrelin, quite opposite. Ghrelin is the hunger hormone. Leptin is the satiety hormone when you're full. Now, this are examples of leptin deficiency. On the left, on mice. This one has no gene for leptin. Regular lab mouse, like black 6 mouse, like this one. Adult mouse, about 25, 28 grams the most. These guys, we studied obesity. We studied diet-induced obesity. So we fed them with like gross diet. It tastes like cookie dough. So the max that I weighed myself, my diet-induced obese mouse, was about 60 grams. That was a record holder. This guy was enormous, just huge. Leptin deficient, for them 60, 70 grams is just like average. They have troubles moving. They're so fat that they paws barely touch the ground. They just absolutely disgustingly enormous, poor fellas. Okay, and they go like this on the regular diet, regular chow, nothing, no fat, very little fat, very little carbohydrates. Okay, just they can't stop. This is the human. So this boy was born leptin deficient. As far as I remember, this picture on the left, that boy was taken when he was 4. He's clean, morbidly obese. He was started on the leptin supplement. I don't know I think those were pills. I don't think you even have to take like injections. I think pills work. I'm not sure. But he was given leptin, and in like 1 or 2 years, he practically came back to normal. So the earlier you start, the better. Okay? So, let me wrap it up. This is the reference tables. Okay, these are the reference tables for your, like, if you want to quickly just glance, is that a peptide? Is that a lipid? Is that something else? You can go there. Very brief summary of what the hormones do. I'm going to post the study guide when I walk out the, well, not when I get to my office. I'm going to post the study guide. Okay? Those of you who never encountered my study guides, don't be scared. They're huge, but most of them are empty spaces to fill them out. On Monday, okay, exam. How about Monday after Super Bowl? I know. Believe me, your micro exam is not that serious. Okay. I have few students that take micro and AP2, and they have 2 exams on the same day. So there are 2 options really. We can meet on Monday. It's up to you. We can meet on Monday next week, do study guide review. Okay, it's going to take us about an hour. And then look at the slides and blah, 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 just monotony stuff and, repeat stuff. And we will do the actual exam on Wednesday, a week from now. And then we can just move on. Sounds better? Okay. drag it down to Monday? Huh? What do you think? Wednesday? We're going to spend Monday on extensive review? Okay. What I think we can do, let me pause the recording.